All right. Thank you. Thank you for coming to this lecture today. So we will cover lecture 9, analog to digital converter today. So as usual, lecture 8 video slides are available in my courses, and today's access code is here. You can also check from my courses lecture slide PDF file. And I'd like to make an acknowledgement for technical discussion and inspiration. Now he is a professor, Yoon Tae-jung. He is an assistant professor at Kyung University who gave a invited guest lecture last time. And CH exercise 7 is out, so please submit a report answering the questions specified in the CH exercise 7. So this exercise is about bootstrapped sampling switch. So deadline is as usual 2 weeks later. So what are we going to run in lecture 9 today? So today we will understand the basic concept of amplitude quantization in analog to digital converter, in short, ADC. And understand the limitations of the baseline sampling switch. So you probably have completed the CAD exercise 5 about the baseline sampling switch, very basic, NMOS and capacitor. So there is a limitation to be used for a generic ADC. ADC is a sampling switch. So we will go through what are the limitations of the baseline sampling switch and learn the basic ideas of bootstrapping or bootstrapped sampling switch. And we will go through live demo, like CAD exercise 5 and 6. So walk through. So this is online. We will go first quiz solution, ADC, amplitude quantization, and bootstrapped sampling switch, and CAD exercise, group discussion, CAD 5 and 6. So for the announcement and the reminder for solving the quiz, please help us to recognize your quiz sheet with a clearer handwriting. Our TAs are a bit struggling to recognize your handwriting sometimes, so it'll be very helpful. So this is a score of quiz 7. So this is available in my courses. Quiz 6 retake score is a bit delayed, but it will be posted very soon, hopefully this week. And this score is now excluding students who did not attend the quiz at all for the quiz 7. And we can see that the average score is pretty much high. So like 13.1. Many of students got a score higher than 10 points. And of course, don't be discouraged. You can also have another round of quiz retake next week for the quiz 7. So this is a very good job. So even one student scored, I think it was 19 point or 18.5, which is very high score. And and then let's go through the quiz 6 retake. Well, probably this happened on today's Monday. And in lecture 6, the mathematical modeling of a track and hold circuit is performed by decomposing its operation into a track component and a hold component. The output frequency response of a track and hold circuit under a 50% duty cycle clock, XTHF, is derived as this kind of a bit complicated expression or mathematical expression, right? And where Xin F is the spectrum of the continuous time input signal, and the Fs is the sampling frequency, and the sinc function is defined in engineering field. We mostly use this format, sinc function. Sinc x is sine pi x over pi x. But sometimes in other fields, sinc function is sometimes also defined as a sine x without pi. But in our engineering field, we normally use this definition. So the first question is this. In the time domain, the track component is modeled by multiplying the continuous time input signal Xin by a specific periodic waveform. Identify this periodic waveform and state its maximum and minimal numerical values. So if you recall correctly, then you may recall this kind of waveform and the mathematical modeling. So we can divide track and hold operation into track mode and hold mode. And for the track mode, it is based on just a very simple ideal switch, right? So in track component, this is just pass-through switch. So if clock is on, clock is high, then switch is on. Then the V in is just transferred to the V out. So that means the gain is equal to 1. Clock is high, the gain is 1. And clock is low. Then we have for the track part, we don't apply anything. So that means we have to set the gain equal to 0. Otherwise, if we set gain equal to non-zero, then the track operation will affect the sound output of the sample and hold operation, as we went through for the theoretical expectation. And you can also find what was the equation about it. So in this case, this is a rectangular or square wave. And this is a waveform, 1 and 0. So in the time domain, the next question, time domain, the track and hold circuit utilize the zero order hold operation, and which captures on instantaneous voltage and holds it constant for a specific duration. Intuitively, does this holding action act as a high pass or low pass or band pass filter on the analog signal spectrum? And briefly explain why based on its time domain shape. So is there anybody who solved this one? This sub question? No? So for the hold operation, once it is kept hold here, so we first capture the signal and then just kept hold as it is. So that means no matter how fast the signal is fluctuating, so let's say the input signal is somehow here in this domain, in this window, it is fluctuating. This hold operation doesn't care. It just it just keeps the voltage when the voltage it is sampled previously at the sampling instant. So this is just a low pass filter. Low pass filter. And this is Y, and time domain shape is as we studied. Let me erase. I studied. This is it, right? Low pass filter because of sinc function. So sinc function has this kind of bell shape around certain frequency, and it touches 0 at x equal to 1, because that means a sine pi over pi, which goes to 0. So it has a bandwidth within certain frequency band, and it goes towards 0, and it doesn't touch 0 for track and hold because of this track mode component. And the next question, derive the approximate baseband transfer function HF XTH X in by retaining only the k equal to 0 term. So the answer is this, right? We already went through how to derive it. You can also do this, for example, by plug in k equal to 0. Then this one goes 1, and this one goes to 1. Here, there is a hint. Sinc 0 is equal to 1, and this one out, and this one doesn't be affected, and this one goes to 1, and this one is also just go out. That goes to hop x in app. So this is a track mode, and for the hold mode, this component arrives, make it alive, and X in F also make itself alive. So here is the result. So evaluate the baseband transfer function HF at F equal to 0 and F equal to Fs. And using these two values, briefly discuss the generic shape of HF. We already have seen here, right? But using the mathematical just a derivation, you can also expect what will be the generic shape, at least for the range of 0 to Fs. So for F equals to 0, which means a DC response, then definitely okay. So definitely this can go to 1 here, and this goes to also 1. That means half times 2, that goes to 1. And for the F equal to Fs, then let me erase here. So F equal to Fs, which is a sampling frequency, then we can plug in F equal to Fs, that goes to sinc half and e to the power of j pi over 2. So for we can solve one by one for these two terms, for the sinc part and e to the power of j pi over 2. For the sinc part, we can plug in simply sine pi over 2 over pi over 2. And the sine pi over 2 is equal to 1, right? So that goes to 2 over pi. And for the e to the power of j pi over 2 can be solved by applying Euler's relation, cosine theta plus j sine theta. Then we can plug in, and then cosine pi over 2 is 0, and sine pi over 2 is 1. That goes to minus j. So here, right? And I think there was some mistake here. J, right? And J. So by calculating the magnitudes, then we can derive this square root 1 over 4 plus 1 over pi square. So calculating the magnitude here. So we can see that this is definitely less than 1, right? So we can conclude that because there is only the continuous values, so we can expect, okay, then the frequency over magnitude will be kind of this kind of shape. And here is a sampling frequency, and the gain is DC gain is 1, as we checked here in this graph. All right, so for the quiz 7, in a continuous time active RC filter, the nominal cutoff frequency is given by this equation, 1 over 2 pi RC. And due to physical chip fabrication, the components experience process variations across lots and wafers, as we discussed in lecture 7. The physical resistance R has a process variation of 25%, plus minus 25%, let's assume. And the physical capacitance C has a process variation of plus minus 15%. And the first sub-question is this. To calculate the expected fastest cutoff frequency, Fmax, in terms of Fnorm, nominal, and express your answer as a simplified expression, and calculate the expected slowest cutoff frequency, Fmin. So you don't need to calculate the exact number, just plug in what are the required numbers in expression. So for the maximum frequency, because it is a 1 over RC, that means the maximum frequency is achieved when R is low value and C is low value. So we can pick up 25% lower value of R and 15% lower value of C here. So that goes to this equation, 1 over. In terms of F nominal, that goes to 1 over 0.75 times 0.85. And the slow frequency case is the same principle. We can pick up 1 over RC, R is high and C is high. That goes to 1 over 1.25 times 1.15. And that is in terms of F nominal frequency. And third question is this. Explain the core physical or circuit reason why replacing the continuous time physical resistors with switched capacitor equivalent resistor ensures a highly accurate cutoff frequency. In your explanation, you must, okay, so let's first look at this one, this sentence first. So because this R and because R and C, both of them has uncorrelated relationship. If we can make this R correlated, this is a problem. Correlated with C, let's say some R plus C, that is correlated each other to C physically using capacitor to build a resistor, then we can make correlation between the two R and C components. So that is a core principle of switched capacitor low pass filter and the switched capacitor filters. And in your explanation, you must explicitly address how the SC filter handles the fact that its physical capacitors still inherently suffer from plus minus 15% process variation. So even if there is a process variation, if we can make sure F is proportional to some constant, C1 over C2, let's say, then even if there is some variation, if we can put the capacitor here, C1, and capacitor here, C2, very close to each other, adjacent to each other, then C1 and C2 are affected by the same process variation within the device level. So that is the core idea about solving this problem. Of course, if we put different capacitors, I mean, let's say we put different capacitors here and here by just going through the different lot level process, then there will be lot level variation. Or let's say we put different capacitors here and here. Let's say the process procedure of making or fabricating capacitor is different. For this wafer 1 and this wafer 2, then definitely wafer level of variation will exist. Or if we put C here and C here, then chip level variation will exist. But if we put at device level, put capacitors very close to each other, this is still in our chip design world, this is too much far away. So let me zoom in here. Let's put capacitor here, C1, and capacitor here, C2. Then there is only mismatch, not the global process variation. In practice, what we normally do is we copy and paste. Let's say this is a unit capacitor. Then if we want to make, for example, 4 times higher C2 value, then we put copy and pasted unit values this way. So it's C2. So the unit capacitors are placed by copy and paste. And if we put this way, of course, then definitely there will be some variation at this capacitor and this capacitor. To avoid this, what we can do is placing, for example, 9 capacitor element, and the middle one is C1, and around 8 capacitors are C2. So this is the case where C1 to C2 is 1 to 8 ratio. So this is a layout level technique. Okay, the next question is this. The AC magnitude response of a RC low pass filter here, upper side, right? For the black one, and a switch capacitor low pass filter, blue one, and the designed cutoff frequencies are, let's assume that around 15.9 kilohertz and 159 kilohertz for the left and right. So this is 15.9K and 159K. Operating with a clock frequency equal to fs equal to 1 megahertz for switched capacitor low pass filter. So AC simulations show that as we approach, sorry about this. As we approach from this cutoff frequency to this cutoff frequency, and this is sampling frequency, more closer to the sampling frequency, 1 megahertz, then it starts to deviate from the ideal RC low pass filter. And let's explain the fundamental operational region for deviation in high frequency magnitude response. Specifically, what a specific mathematical function shapes the high frequency magnitude response of the switched capacitor filter. So this is a RC low pass filter. For the switched capacitor filter, it goes to downward, right? So what is the mathematical expression? The answer is sinc function, right? So we studied about the sinc function derivation in lecture 7 by comparing track and hold operation and sample and hold operation. So what is the theoretical magnitude of the switched capacitor filter exactly at the sampling frequency fs? Of course, the sinc function has knowing values at sampling frequency. The answer is 0 in linear scale. In dB scale, minus infinite. So in lecture 7, we derived the cutoff frequency of the switched capacitor filter as follows. So Fp equal Fs over 2 pi C1 over C2. On the right graph, the response starts to deviate from the RC low pass filter, even around 100 kilohertz already here in this region, even at here. So from the graph, briefly explain the limitation of this equation. Of course, this equation cannot model precisely the high frequency cutoff frequency expectation. So as we approach from a low frequency design of cutoff frequency to the high frequency, then it starts to deviate. And one physical circuit effect between C1 and C2 was omitted in the derivation of the equation. So we discussed about this lecture 8, right? So we only modeled this guy as FC without thinking about C2's effect when we build the switched capacitor low pass filter. So we ignored the loading effect of C2 and then derived this equation. And if you remember, then in lecture 8, then we derived the more precise and accurate switched capacitor low pass filter cutoff frequency equation, and we show the simulation result is more precisely following this curve, RC low pass filter. So the answer is we ignored the loading effect of C2, or you can also think about it as a charge sharing, which is charge sharing it means when we put Q3 equal to Q1 plus Q2. Remember in the last lecture? So Q3 is C1 plus C2 V out in phase 2, and Q1 is C1 times V in, and Q2 is C2 times V out. So we used this charge conservation law, or you can also call it charge sharing, that shares the charge when we want to derive the Z-domain analysis of switched capacitor filter cutoff frequency. All right, then let's move on to the next section of today's lecture, analog to digital converter, ADC. So we can first start talk about amplitude quantization. So in lecture 1, if you remember, we discussed about four variants of signal processing circuits by dividing level-wise, continuous level or discrete level. For the time-wise, we can divide as a continuous time and discrete time by having the boundary between continuous time and discrete time, whether we sample the input analog signals with a certain frequency, or you can also call it a certain time period. So our journey so far, what should be considered before we sample, as we discussed last time, and our journey so far, what happens after sampling? And the next question is this: how can we quantize amplitude? So that will be the remaining part of this course in lecture 9, lecture 10, lecture 11, lecture 12, towards our ADC output. So amplitude quantization. So this is the waveform of track and hold operation as we studied last time in lecture 7 and lecture 6. So we put sampling switch and the sampling capacitor, and we put here quantizer. We will go back to this notation again. And let's assume that we want to quantize, just put the levels and divide the levels using very, very simple one threshold of criteria. So let's put just one threshold, and if the input signal is above the threshold, we call digital output as a 1. And if the input signal is lower than the threshold, we call digital output as a 0. And here we assume that reference voltage about 1 and 0 for the full scale range here. So this threshold is exactly half of reference voltage. So we assumed here Vref is equal to VDD, the supply voltage. So in this case, we call VFS as a full scale range. So full scale range here. This is in this case, for this slide, full scale range is equal to free reference. But there is another case, full scale range is not equal to free reference. I will talk about it later. So in our case, we can build this kind of a quantizer and then sampling switch that goes to 1-bit ADC. So 1 bit here means here 1 goes to 2 to the power of 2 to the power of 1. That goes to typical digital representation of our data. That can result in 2 to the power of 1 is equal to just 2. That means there are only 2 codes and there is 1 threshold, the 1 criteria. So 1 step here, we call this one as a delta, 1 step. Delta is now equal to Vref over 2 to the power of 1, because there is only 1 threshold. So we call this as a delta as a 1 least significant bit, 1 LSB. So we call this minimal step of the ADC as a 1 LSB. So this is the case of, this was the case of 1-bit ADC. Then if we move on to slightly different bit, for example, from 1-bit ADC to 2-bit ADC, then there are 2 to the power of 2 equal to 4 digital codes, and there are 3 thresholds. To represent 4 codes, then we need 3 thresholds. 3, right? So the code starts from, in binary format, code starts from, you probably have run this kind of binary format in your programming courses, right? 0, 0, 0, 1, 1, 0, and 1, 1. And we call 1 step as a LSB. Delta is now it's Vref over 2 to the power of 2, which because we have 4 codes here, 4 codes. And what about the 3-bit case? Then the principle is the same. We just increase from 2 to 3, 3-bit ADC, and to 2 to the power of 3, there are 8 codes, 0, 0, 0 to 1, 1, 1, by increasing by 1 as a binary representation. And of course, if we want to represent 8 codes, then definitely we need 7 threshold, right? And still we keep the definition as the same. 1 LSB delta is equal to brep over 2 to the power of 3, because we need 8 codes. So this is a full scale range and brereppers. But of course, there can be some cases. I mean, this case is definitely the input signal is as large as from VDD to 0 volt. So its analog input signal is quite large signal. But you probably have remember how was it your amplifier design, CAD exercise 3, such that its input linear range or input DC input range that goes to, if we set as a buffer, then the input DC range is equal to output DC range, because output follows the input, right? So we could not achieve like very, very wide input DC range or output DC range because of the transistors limitation, VDS limitation. So let's say we we have more practical situation. So input range of ADC, let's say in this case, is equal to the output range of the buffer here. And these range are unused range in this case. So the input signal is only going to like just 75% of VDD and going down to only as low as 25% of VDD. Then the 75% to 100%, 0% to 25% of the VDD, those ranges are all unused. So that means we are wasting these digital codes, right? 001, 000 for 3-bit case, and 111 and 110. So digital code 7, 6, digital code 1 and 0, those are wasted. So only 2-bit codes are used within this range in practical cases. So this happens, for example, as I said, if you recall CAD exercise 3, CAD exercise 2, and 2 and 3. So we put unity gain configuration for this amplifier, and this is limited by the transistors, PMOS, VDS, NMOS, VDS. Definitely it requires some amount of VDS to make sure it is in saturation mode, for example, 150 millivolt, 150 millivolt. So even if you buy very, very expensive OP amp in just a market, Texas Instruments or analog devices, then the OP amp's output range is not touching VDD to 0. There is always certain amount of millivolt. For example, 10 millivolt or 5 millivolt is sometimes 100 millivolt is limited for the VDD minus 100 millivolt or VDD minus 10 millivolt. The lower side, like 10 millivolt or 100 millivolt. Because of, we are building OP amp or whatever analog circuits using PMOS and NMOS. So definitely that requires some amount of output DC range is required at the transistors at the VDS. So instead of wasting these digital output codes for the ADC, we can also think about this way. So when we squeeze, reduce the reference voltage, not touching VDD, let's put reference as 75% of the VDD, then we can call vrep P and the lower side as a vrep N. And let's say we increase the lower bound to 25% of the VDD. Then we can make use of all the 3-bit digital code, right? We can make full use of 3-bit digital code for the input range. So this way, we call full scale range as a vrep P minus vrep N. So this is another definition. In general, this is a more precise definition for many ADC designs of other cases. So you can also think about this way of interpretation when you have to use ADC for building your own PCB for robotics project or other types of electronics project. So in this case, the step LSB is defined as a full-scale voltage over 2 to the power of 3, which is 8. So it goes to, better utilization of full-scale range, VFS, which is good, but there are cons. I mean, on top of VDD, for example, this is normally required. Let's say we put this analog circuit, then somebody needs to provide VDD. When we think about our cell phone, iPhone or Galaxy phone, whatever they are, Nokia phone, then it requires regulator and the battery. So this is a normal, very, very generic case of how we provide supply voltage to our analog circuit, and it is also true for digital circuits. But now we need another regulator to provide either from a battery here. Let's put it this way here. So this goes to reference P and reference N. So we need additional circuits for providing reference P and reference N for the ADC design if we set this way of full-scale definition. So you need to take a bit careful when you want to design ADC in terms of system-wide design perspective. So anyway, in general, not thinking of just a 3-bit ADC specifically, when we define as a n-bit ADC, then the number of codes are defined as a 2 to the power of n. It is just a very, very generic definition of digital code, digital representation. And the number of threshold is definitely 2 to the power of n minus 1 threshold. And one step LSB is defined as a full scale over, sorry, there is a mistake. This is n, and this is n. We full scale over 2 to the power of n, we reference over 2 to the power of n. And the code ranges from code 0 to code 2 to the power of n minus 1. And we call this part as a quantizer. So as I explained, this part is still analog. And after quantizer, this part becomes digital. So here, after sampling the analog signal, on top of sampling, if we put quantizer, then now it becomes as a digital data. And we call this whole bunch of things, normally, sampler and the quantizer as a whole thing as a ADC, analog to digital converter. There are some other types of ADCs that we don't sample at front. For example, this is an input, we receive some continuous time integrator and put sampling and quantizer, let's say Q, and we make a loop this way, plus minus, which is a negative feedback loop. There is also this kind of ADC, which is called as a delta sigma ADC. But in this slide, we call it more generic ADC that includes a star ADC, a successive approximation ADC, which we will discuss later lectures. Okay, then what happens after quantization? So I just drew the quantization, the threshold only in this graph. I didn't draw the ADC output waveform, not yet. So let's go through that part. So let's go back to a more simpler expression about ADC. Let's suppose that we are examining only 1-bit ADC. then we've set the threshold here as a half pre-reference. Then the ADC output will be definitely this one. I mean, this upper part must be equal to 1 because it is over the threshold. So this is the ADC D out that goes to 1. And as we go through for the clock signals, we are producing ADC output. And here, what I want to highlight is this. After sampling means that we first track analog signals. And then at the end edge of the track, we sample the input analog signal and then keep as it is. We call it as a hold operation. During the hold operation, here, this is the hold operation, right? Here. During the hold operation, the ADC quantizer runs and do their or its job. And the output is produced during the hold window. So this is how I expressed ADC D out. And then let's follow it. D out at the clock's falling edge, the hold operation is processed within the clock low signal, right? Low window. And within the clock's low window, ADC output is produced. And let's go one by one and so on and so forth. For the analog input signal is over the threshold. Indefinitely is always data equal to 1 for the 1B ADC. And then we are now experiencing the situation at the next hold window, and it goes down to digital output data as the 0, because at the holding phase, there is a mouse point here. At this hold window, we see the input analog signal is over the threshold, and the next hold window, we see the output. Input analog signal is lower than the threshold. Then our output digital code must be 0. And this way, the ADC works and produces digital output code and so on and so forth. So this is a principle. And if we go to 2B ADC case, then you can simply think about it, right? So for the threshold, we first set the threshold for the 3 threshold here for the 2B ADC. And within the hold window, first hold window, second hold window, then we produce ADC output, and I want to highlight this one. So we produced ADC output here, and then we keep the ADC output until the next hold phase. So because this is a digital code, it doesn't change during the next phase of track operation. So we produced ADC output, and it doesn't change during the next phase of track operation. And then now the next hold window, it experiences the input analog signal is larger than the highest threshold. Then we need to produce output digital code as a 1-1, right? And this way. Again, during the next track phase, it doesn't change. During the next track phase, here, it should not change this way. So once we produce the 1-1 output, the ADC output during the next track phase, it doesn't change. And because the analog input signal, it experiences within the last threshold and the second last threshold, we produce digital output as a 1-0. And it goes and so on and so forth this way. And we can think about this principle as the same for the 3-bit ADC case. For the 3-bit ADC case, there are 7 thresholds, and there are 8 codes from 000 to 111, from digital code equal to 0, digital code equal to 7. Then you can do so. For example, here, for the analog signal within the code of 1000, then produce a digital output, and it must be kept as it is during the next track phase. It doesn't change the output digital code. So as ADC bit increases, you can see that the quantized digital value more precisely represent the analog input. So this red curve is becoming more closer to the input analog signal, the navy or blue, compared to this 2-bit case. This is a 3-bit case. 2-bit case, 3-bit case. So we call this kind of 3-bit or 2-bit and the 3 and 2 of the 3-bit and 2-bit as ADC resolution. So as we increase the ADC resolution, 3-bit in this case, in this slide, then digital output code definitely goes to more closer to the analog input. So this is the fundamental. And in reality, the quantization requires a finite conversion time. So this is a real world circuit. So it cannot be processed. I mean, it cannot process the input signal or just electrical signals with just an instant, window. It requires some conversion time to do its job. So we model conversion time as this way, so such that its red curve is slightly went toward, right side. So this is a more realistic ADC output. So it becomes more, complicated to have a look of what is happening. I mean, there are random staircase signals, but this is how it works. So in reality, D out becomes valid only after some delay. Here, conversion time, following the hold phase of the track and hold operation. So the signal chain goes this way. We first track the analog input, and we sample and then keep it as it is. We call it as a hold operation, and we do the quantization, and now we get the D out here. So whole process is, simplified within this graph. And typically, what we can do is that we set another output signal called ready, or sometimes it's called as the end of conversion. So after quantization is completed, we raise the 1-bit digital output as a flag. Okay, ADC work is done, saying that end of conversion, EOC, or ready. ADC output is ready, such that for the following digital signal processor can capture the ADC output. So this is how it works normally. And when we represent the ADC output codes in terms of digital bus, you probably have seen this kind of waveform when you run the digital microelectronics course Verilog simulation. Then you probably have seen this 100, 101 here, 100, 101, and 110 and 111, and so on and so forth. So this is a digital bus representation of D out. Okay, so probably we can have a short break for 5 minutes. So we will have a break until 9:08. And sorry about the Presimo platform. It has not been updated. Our TA will update as soon as possible. And if you have questions, please keep it. And then I will let you know when Presimo is ready. Okay, so let's move on. So we will move on to bootstrapped sampling switch or bootstrapping sampling switch. Those are the same principle. Okay, so we first let's have a look on ADC input range discussion. So we have checked that when we use preceding buffer of the amplifier, then there is a certain amount of input range and there is a certain amount of unused range. And this is a situation for the 3-bit ADC case for quantizing the input analog signal and the digital output code is there. So now, of course, we can keep reference as a VDD without using additional circuits for VDD plus P and VDD plus. Do you need some cover of this sunlight? Is it okay? Okay. So yeah, of course we can just keep it as it is and then just increase ADC bit ADC resolution. For example, increasing the quantizer bit from 3 bit to let's say 5 bit or 4 bit or 6 bit. But the thing is that I will discuss in later lectures. Increasing ADC resolution is not easy. It's not easy. So a better approach is to maximize the utilization of VFS, full scale range, this blue navy graph, by increasing the input swing. So before we touch the ADC, quantizer, or sampling switch, it is better to increase here at the buffer side. So buffer output swing. Of course, there are some other considerations. These days, many things are arising because of advanced technology nodes. So this was a kind of golden standard so far. I mean, not so far, until like 180 nanometer or 65 nanometer, that kind of ADC and analog front-end architectures. But these days, different point of views are arising. For example, this is a very nice talk. You can have a check at YouTube about Professor Bromnauta's talk about system-wide consideration about how important it is to think about ADC's power consumption that is affecting all the preceding chains for wireless communication circuits. So increasing the input swing helps ADC's range utilization only. So when we think about ADC only, it is helpful for increasing the input swing. But in general, for the system-wide, it may not be the best solution for increasing the ADC's input swing. So it depends on what system you are thinking about. So it is not always true to increase or maximize the input ADC's input range. But in general, in this lecture, we will think about it as a more classical domain of ADC's utilization of input swing. So it depends on your system wide or application wide differences. So for example, let's say we are designing like wireless communication circuits. Then for the receiver side, we can put low noise amplifier at the front end, and we put buffer, and we put sampling switch, and we put quantizer to build the ADC. So in this way, if we put the amplifier, then we can maximize the input swing like this. From here, low input swing to large input swing, right? But yeah, the input swing can be maximized by front-end amplifier. And the situation will be like this. I mean, it is not aligned well, but you can think of this kind of very large swing is the same as amplitude for the sampled analog signal icon. But there is a design issue when we maximize the input swing. This is part of the state exercise you have gone through. So anybody can guess? What is a design issue you can expect if we maximize input swing like this? Sorry? Stability? Unfortunately, it's not related to stability. Sorry? Overlapping. Overlapping? From where to where? Like breakpoint. From this one to this one to this one? Unfortunately not. Yeah, and then why this problem? What's the problem? Well, it can properly then get 111 result. Yeah, 111 result and what? This what? Sorry? Distortion because of which phenomenon? It gets compressed by ground. Yeah, grounded VDD. And who causes that problem in this circuit? It was part of your CH exercise. MOS transistor. This guy. Yeah. And which CAD size? Do you remember? Yeah, CAD5. Right. So you have verified DC input range of CAD exercise 5 about this baseline sampling switch. And you probably have seen that there is some curve flat and then suddenly goes down for the DC input range, PAC DC input range, right? And I'll explain more detail about what is happening in this switch. Before we move on. So yeah, we have 4 people. Nice. So here, this is a sweet chocolate. Here. So thank you. Thank you. So I didn't buy this from Finnish supermarket. I mean, it's not from S Market or Co Market, K Market. It is directly from Zurich, Switzerland. that my previous supervisor gave me as a gift. Thank you, Sichi. Anyway, so let's go through this ADC input range. So this is CAD exercise 5, gain versus DC input range curve. And this is just screenshot capture directly from one of your reports that scored perfect score for the CAD5. Nice job. So we could find that 3 dB point is there. And as we increase the DC input DC voltage, and after running PSS and PAC simulation, you could find that, okay, there is some kind of, attenuation. I mean, going to the low DC gain cases. So this is a design challenge because when we apply large input at the input side, then this is a situation. When we apply large input, it goes to very, very, how do I say, wide swing fluctuation that changes every single moment DC operating point by this large swing signal. So when the signal swing is touching close to VDD, then its operating condition is different from when it touches too close to ground. So this is the problem because here, this part experiences low gain that goes to signal distortion. For the peak point of this signal, then this part, within the low gain part, it squeezes out to a little bit low gain. And for the lower part, low amplitude, low voltage value part, it experiences as the DC gain equal to 1. So this is a problem. So when we model this sample and sampling switch as a MOS transistor and the capacitor, then we can model this as a on resistance, R on. Here you can have a check of this was a part of extension of part of basics of IC design course, and you can further check from Professor Lazabi's very nice YouTube lecture about R on equation here. The point is this: so on resistance of the MOS transistor in triode region, linear region, can be expressed this, right? Proportional to 1 over overdrive voltage, VGS minus V threshold. The gate voltage here, when clock is on, clock is high, then it goes to VDD, gate voltage, and the source voltage is V in. So VDD minus V in minus V threshold. So this means that its on resistance is changing according to V in value. So when V in value is high, then the on resistance is I think it's it goes to low on resistance because there is a minus and in the denominator. If the V in is low, then it goes to low resistance. So let's suppose that we are here, point here, and the value is low, and this is a VDD. Then situation is this: the low R on resistance of the switch is low. But as we move on to the high value, then situation is this: the on resistance is becoming to high value. That goes to input dependent R on that goes to distortion in sample signal, that goes to low or non-linearity. We can discuss about this linearity thing. What is linearity thing in the later slides? But you can intuitively understand what is going on, expressing squeezed out at the high values of sine wave. So to tackle this issue, we can put two switches in parallel. One is MOS switch, and the other is PMOS switch. One switch, MOS clock, the other switch, PMOS. You can flip the polarity to the clock bar that goes to R on N parallel R on P. So MOS switches on resistance, PMOS switches on resistance. And you can see that as we increase V in, then on resistance reduces for the MOS switch because its VGS for the MOS switch is decreasing as we increase V in. The source voltage is going up and up and up and up and on. So R on is increasing, and it touches until it fully, turns on. In theory, it turns on. It turns up. Sorry, it turns up the MOS switch as it touches VDD minus V threshold MOS switch, because this is the point where VGS equal to V threshold for MOS switch. And similarly, for the PMOS switch, from V in, high value, as it touches more and more and more and low value, then the clock bar is, here is 0. And for the PMOS, VGS must be ensured. So VSG. VSG. So source voltage should be higher than the gate voltage. But as we decrease V in voltage, then definitely as it touches V threshold of the PMOS, then PMOS turns off and its on resistance goes very, very high value. So if we put in parallel, then PMOS plus MOS plus PMOS switch, then it goes much, much better situation. So at least within this range, we can expect, okay, V in doesn't squeeze out that much, so low R on across the wide V in range can be achieved. But is this the best we can do? So that was the question, and related to bootstrapped sampling switch. So the concept of bootstrapped sampling switch is this. When the switch is up, then we want to drive the gate of MOS switch as the ground to fully turn off the signal, no matter how the V in is large from swinging from ground to VDD. As we put a gate voltage as the 0, then definitely this switch is off. And when we drive clock signal as the high value to make switch to turn this switch on, then we want to put some sort of VDC, which is a DC voltage that is shifted from V in to V in plus VDD. The plus minus sign is there. So we want to make sure the gate voltage here, VDD plus V in. If we can make sure this is happening, then always VGS value, the gate voltage and the source voltage, is ensured as VDD, no matter how V in is moving, high value or low value. It is kept as the constant values. So what we can do this way. So this is a concept of bootstrapped sampling switch, and let's go through it. So VGS equal to VDD across all V in range can be achieved. This goes to input independent. So it was input dependent R on. Now it is input independent R on. Yes, but how? So this will be the part of your CED exercise 7. So this is a conceptual diagram of bootstrapped sampling switch. So we put bootstrapping cap here, CBT, let's call it CBT, and there are 5 switches. So those 5 switches are required to provide some DC voltage, VDD. So let me explain what is happening. So to make sure switch is up, we want to drive, this MOS to ground voltage, right? So we put one switch for that purpose, simply driving ground, and we put another switches, one switch and the other switch, to charge this capacitor as a VDD, such that we can think of this capacitor working as a battery, some sort of battery. And then now we attach this battery to input side. So it is working as a VDD charged battery, such that its voltage across capacitor is conserved as a VDD. And if we connect, it was previously connected to ground here. Now we connect the bottom plate as a V in. Then definitely this, if we assume that voltage difference across this capacitor is constant, then VDD is provided from bottom plate to top plate. V in plus VDD is provided at the gate. So this is a part of charge conservation law you have seen in previous lecture about switched capacitor filter. So charge conservation law is that Q equals CV. So here, this is a CVT, and V is VDD. So this is a VDD, and this is a ground, right? And let's assume that this charge is conserved. So charge is not lost. Of course, there can be parasitic cap here and parasitic cap here. You will experience this kind of parasitic caps during your seed exercise. But at this moment, let's forget about this. And let's approximate there is no parasitic cap. Then if we assume charge is conserved and it is not affected by any other things, then the same charge will be stored here, charge. Q equals CV. That means the voltage across here is as the same, no matter how the bottom plate is different, no matter how top plate is different. So that is the charge conservation law, and this kind of action is technically called as a bootstrapping action. Okay, so this is a basic principle and conceptual circuit. Of course, we use the ideal switches. It's not transistors. It's the ideal switches. So in terms of transistor level implementation, how we can implement or realize this practical circuit using transistors. So for the easiest part is, this switch off case. This switch can be replaced with MOS there. And I specifically put clock bar here because for this MOS, we want to make this switch off. So that goes to clock bar, the inverted polarity. And the next thing, we can realize this switch. So for this PMOS switch, there is some consideration required. So if we just connect, here the body is assumed to be ground without any notation. Body is assumed to be ground. And I specifically connected the body voltage of PMOS as this node. This is because this P node swings from VDD to V in plus VDD. So it was VDD here and here. VDD plus V in. So let's say that V in is very, very close to VDD. Then it is approximately 2 times VDD. So this can be very stressful for the transistors. So in our process technology, we use 1 volt supply voltage. So that means that is the maximum voltage that this transistor can tolerate. Of course, there can be some gathering. For example, the fabrication of device engineers make sure this transistor can endure as high as 10% higher voltage, for example, until 1.1 volt, 10% margins there. But normally, when we say our technologies maximum supply voltage is 1 volt, then if we plug in like 5 volt, then your transistor, your circuit will be dead. It will just blow up. That is the maximum voltage it can endure, it can tolerate. So that is specified for the VGS, VDS, and also VBS, the bodies to source voltage. So for this PMOS, if we just drive Vin plus VDD and then connect this one to the VDD, this one to VDD, then this is a part of the discussion in later slide. But in this case, if we set VDD, then the PMOS transistor can be implemented as a PNP case. For example, this is how the PMOS transistor is made. This is a gate, and we apply N-type diode here and P-type diode here, voltages, so such that we want to make sure N-type diode is applied with the highest voltage for the transistor, or at least higher than the P-type diode transistor voltage. So in this case, if we apply Vin plus VDD at the source and the body voltage as a VDD, then definitely source voltage is higher. Then this flows the current no matter how we control gate voltage, whatever it is. There is a certain amount of current flowing due to PN junction. So we don't want that kind of situation. So we tie this body voltage to source. So those are here, those are connected. Such that this VP will be same as body voltage. Then we can fully control by controlling the gate voltage. This is the situation. And when the clock bar is 0, then P and X will be connected by switching on the transistor. We will talk about this maximum rating in the later slide. And the next thing is, it is much more simpler. For this case, we are not controlling high voltages in this region, right? For the bottom plate of capacitor. So only the node here, this is a high voltage, this node. So the remaining part, this part, does not experience high voltages. So we can just keep as it is. We don't want to worry too much about the MOS transistor safety. So we can just put MOS transistor there. And another PMOS transistor, as the same discussion, we don't want PN junction is turned on. We want to tie body voltage to P node, which is the highest voltage. And the gate voltage is connected to the X node. So we may think about connecting this voltage as a clock bar, of course. But in that case, then let's say when we want to drive this one to 0, that goes to PMOS to turn on. This is the case. This is okay, but when we drive clock bar equal to VDD, then again, if we drive VDD, then source voltage is higher, right? So in this case, we want to turn this transistor up, switch up, but because of high voltage, it cannot be turned up. So we want to derive gate voltage to X node to make sure this transistor as a switch is turned up during the switch on phase. And the remaining MOS can be connected this way. So X node is the highest voltage, such that we can connect gate voltage of this transistor as the highest voltage. We can also think about connecting this node as a clock or clock bar. Then if this node goes to 0 volt or VDD, then as V-in increases to VDD, then this switch cannot be turned on because VGS is small. So we want to connect gate voltage of the MOS transistor to highest node, which is X node. Yeah, then let me go back to the safety discussion. So we don't want this transistor to, blown up, it boomed and broken. So we can derive this transistor's VSG to the more safer condition. So here, this is the source voltage. This is the gate voltage. Then the VSG goes as high as V-in plus VDD if we just derive this one as a clock bar. When this voltage is 0, then P node is V-in plus VDD. Then if the V-in is VDD, then V-in plus VDD goes to approximately 2 times VDD. Then this transistor may be dead if we derive bootstrapped switch in this gate voltage condition. So we can realize this way. So it looks like complicated, like from here to there. But the core concept is this. We want to make sure the gate voltage swings VDD or V-in, such that when this voltage kept as a VDD, then transistor turns off. When gate voltage is equal to V-in, then the voltage difference between this voltage and the gate voltage is ensured as the VDD. Then this transistor can be turned on without worrying too much about deriving VSG is 2 times VDD approximately. And then we can add another transistor. This is necessary because in this case, we put some kind of inverter here. But in this case, if we drive using the clock signal, such that, let's say we want to drive clock as a VDD, then this is connected to V-in. If V-in is very close to VDD, then this transistor, again, will not be turned on. So we put another transistor. That gate is connected to Vx node, which is as high as V-in plus VDD. So this PMOS gate can be fully driven, either V-in or VDD values. And other safety measures are here, MOS transistor. So in this case, Vx node is as high as 2 times VDD if V-in is as high as VDD. Then VDS of this MOS transistor is too high, 2 times VDD. So we don't want that kind of situation. Otherwise, this transistor will be dead. So we put another transistor as in series. You can check the transient simulation waveform from exercise 7. If we connect 2 transistors in series, then there is a resistance divider. If we set the transistor size as the same, that even if there is a 2 times VDD, then this middle node is almost close to VDD, such that VDS of each transistor is ensured as high as VDD only. So this is a safety consideration about this bootstrapped sampling switch, and VGS equal to VDD. Of course, all input range can be ensured. This is an input independent that goes to input independent our own switch, switches on resistance. And there are other more complicated circuits about this bootstrapped sampling switch. For example, it can be boosted as high as 2 times VDD for the VGS of the sampling transistor, 2 times VDD. There are some other people who tries to 3 times VDD for low voltage ADC design. And if we want to make sure there is minimize the leakage current, we want to derive the gate voltage as the even negative value. So not about 0 volt, we can also derive this gate voltage as a negative VDD. then the leakage current is reduced. So that kind of techniques are also existing. You can further check by reading this paper, which is out of scope for this course, which will be helpful for your research, master thesis, or for example, or a PhD work, or even you enter industry and do some circuit design. Anyway, this is references and